In this video, I will give a brief overview of 10 different topical areas, how they are performed in SAS JMP, and how they are applied in an industry setting. To start, the analysis of variance, or ANOVA, is used to analyze the difference among three or more groups. Based on the Fisher distribution, ANOVA incorporates a continuous distribution in order to analyze the variance. The performance of this analysis is very similar to performing multiple two-sample t-tests. However, it is more conservative, resulting in less type 1 errors, that is the rejection of a true null hypothesis or a false positive. When using ANOVA, the null hypothesis is that the difference between the sets is set equal to 0. In other words, the null hypothesis is that we assume there is no difference between the sets. Using the company's sample data set, we will perform a one-way analysis of variance in SAS. This is done by selecting Analyze and Fit Y by X. Select the continuous variable, profits, as the Y response, and the categorical variable, size, as the X factor. Next, select OK and choose Means ANOVA. Using ANOVA, the null hypothesis is that there is no difference between the profits of each of the three sizes of companies. Being that the probability greater than F value is less than 0.05 alpha, we reject the null hypothesis. In other words, we are able to conclude that there is a difference between at least two of the sizes of companies. The bivariate analysis tests the difference between two sets of data, or tests the empirical relationship between two events or variables. This analysis assists in determining to what extent it becomes easier to predict a value for an unknown variable when another variable is known. Many times a contingency table is used in compilation with a bivariate analysis in order to more closely examine counts of within each of the variables and how they are related to one another. Using the growth sample dataset, choose Fit Y by X and select X and Y as both continuous variables. In this case, we use ratio as Y and age as X. However, this will not affect the result. After fitting multiple lines, we are able to use the R-squared value to determine which line fits the model the best. Here we can see that a polynomial cubic line is the best fit for the model, being that the R-squared value is approximately 0.94, while the linear fit R-squared is approximately 0.82. As you can see, as age increases, the ratio also increases. With this curve, we are now able to predict a person's age based on the known growth ratio, similarly with growth ratio based on their age. When performing a chi-squared test, we use a categorical response and predictor. This test is used in order to determine if there is a significance between the expected or predicted frequencies and the frequency that actually occurs. This test determines how likely the observations are, assuming that the null hypothesis, that there is no association between the variables, is true. The chi-squared test is based on a p-value that determines if we should reject or accept the null hypothesis. This being said, if the p-value is less than the alpha, we should reject the null hypothesis and determine that there is a significant association. Here we will use the carpool sample dataset. In order to perform a two-way chi-squared in SAS, we should select Fit Y by X and choose a categorical variable for the factor X as well as the response Y. In this case, we will choose size as Y and country as X. Displayed is a mosaic plot that we will discuss shortly. Below the mosaic plot, you can see the contingency table, which displays the total count of occurrences for a person in each country owning each categorical size of car. Below the count in each box, the total percentage is displayed, followed by the percentage per column and the percentage per row. Being that the chi-squared test is so heavily dependent upon the p-value, we are able to determine that there is a significant difference in the probability of purchasing a particular size car, in a specific country, being that the probability greater than chi-squared value is practically 0. The mosaic plot is based on the chi-squared test and is a graphical method for visualizing data from two or more categorical variables. In the previous example, we used the carpool sample dataset to perform a chi-squared test. Here, we will interpret the produced mosaic plot. Using this plot, we are able to determine the proportion of the size of cars owned by individuals and if these proportions differ dependent upon the country in which they live in. In other words, this plot displays the marginal distributions of country versus car size and the contingent distributions of one variable at a particular value of another. A few results become visually evident when observing this plot. For example, in Japan, there are very few individuals that own large cars, while the majority own small cars. The mosaic plot allows the user to visually estimate that in America, each of the sizes of vehicles is split rather evenly, meaning approximately a third of the sampled people own a large car, a third own a medium car, and a third own a small car. Another example producing a mosaic plot is using the sample data consumer preferences in SAS. Here we fit y by x and select two categorical variables as the x factor and y factor. We can visually estimate using the mosaic plot that about 50% of not single individuals have school-aged children, approximately 25% more of that of individuals that are single. Similarly, approximately 75% of individuals that are single do not have school-aged children. A design of experiments, or DOE, uses linear regression to produce multiple variations of the production of a product and predicts the outcome of these variations. A DOE designs the method that tasks may be completed in order to explain the variation and attributes of the resultant. This is often used for experiments that the design is directly associated with the variation in the resultant. Using a design of experiments, we introduce change in the variables in order to change the result. The change of an independent variable is generally hypothesized to result in a change in a dependent variable. In order to create a custom DOE in SAS, we select DOE and Custom Design. Here we have determined that we would like to minimize the number of defects in a product. We now enter each of the variables that may cause defects, such as a continuous range of time that the product is heated in a manufacturing facility from 3 to 6 minutes, and the categorical variable of which 3 types of plastics are being used, and lastly, the discrete number of times that the plastic is heated. With the table produced, we are now able to perform each of these experiments using the predicted variables. For example, using the first experiment, we will heat the manufactured product for 3 minutes using plastic type 1 and reheat 3 times. A response surface method, or RSM, is a type of design of experiments and is used for optimization to find minimum, maximum, or match target. An RSM is used to model a quadratic surface to continuous factors. One method to estimate a first-degree polynomial model is to use a factorial experiment or a fractional factorial design. This is sufficient to determine which explanatory variables affect the response variable of interest. Once it is determined that only significant explanatory variables are left, then a more complicated design, such as a central composite design, can be implemented to estimate a second-degree polynomial model. The most popular response surface method, the central composite design, is illustrated in the figure shown. A central composite design builds a quadratic model for the response variable without the use of a 3-level factorial design. The design consists of a single center point and multiple axial points. Each point represents a design of the experiments. At each of the axial points, one factor is set to the axial value, either the maximum, minimum, or matched target, while the rest are set to 0 or the midpoint. The response surface design examines the relationship between several explanatory variables and one or more response variables. Oftentimes, after the experiment is performed, linear regression is iteratively used to obtain predicted results. To produce a response surface design in SAS, select DOE and Response Surface Design. Using a similar example as previously, we will produce experiments that attempt to minimize defects. Here we will input 2 continuous factors, time and weight. We will then select the central composite design, and a table of the experiments is then produced. The column called pattern identifies the codings for the factors. It shows all the codings with a plus for high, minus for a low factor, a lowercase a and an uppercase a for low and high axial values, and a 0 for mid-range. For example, in the first experiment listed, the high axial point of the time and mid-range for the weight will be used. A logistics regression predicts the probability that an object belongs to a class. The result or dependent variable is ordinal, meaning rated or scaled categories, or true or false binary. An example of an ordinal response may be a satisfaction survey asking the question, how satisfied are you with the treatment? Or a binary response being, are you satisfied with your treatment? A logistics regression produces an S-shaped curve that extends from 0 to 1. This describes the probability of true or false based on the known variable. Using a logistics regression, we are able to describe an object based on an input variable. A multinomial logistics regression is used when there are more than two outcome categories, such as did the medication treat the infection and did the treatment come back. Furthermore, logistics regression is an example of qualitative response and discrete choice modeling. The binary logistics model is used to estimate the probability of a binary response based on one or more predictor or independent variables or features. It allows one to say that the presence of a risk factor increases the odds of a given outcome by a specific factor. Logistics regression is not a classifier, meaning it does not perform statistical classification. However, the regression simply puts models' probability of output in terms of input. Once again, using the carpool sample dataset, we will produce a logistics regression in SAS. First, select fit y by x and select a categorical variable for the y response and a continuous for the x factor. Here, we will use type as the categorical and age as the continuous. The bottom curve represents the predicted probability that for a given age, someone will buy a family-type car. The second curve represents the probability that someone will buy a family or sporty-type car, and the distance between the two curves represents the probability that someone will buy a sporty car. The distance between 1 and the top curve represents the probability that someone will buy a work car. The purpose of a control chart is to monitor process variation. By monitoring using control charts, we are able to filter out typical or routine variation, allowing for the manufacturer to determine if a process is stable and predictable. A routine variation may consist of humidity and minor machine maintenance needs. There are three primary types of control charts, these being the X bar chart, which displays the means of each subgroup, the R chart that displays the range of the subgroups, and the S chart that displays the standard deviations of the subgroups. If the R chart displays that the process is out of control, then the X bar chart will be extremely out of control. This being said, we may be unknowingly out of control looking at the X bar chart. This is possible if a process has a high variance, but all of the points meet in the middle, creating a mean that displays as controlled on the X bar, meaning we would not be aware of the process being out of control unless we analyzed the R chart, seeing as it displays the range. Thus, a typical analysis shows both the process mean and its variability, with a mean chart aligned above its corresponding R chart or S chart. The following are characteristics that may determine if a process may be considered out of control. If a single point is outside the control limits, for example, being above the upper control limit, if 2 out of the 3 successive points are on the same side of the center line and farther from 2 sigma from it, if 4 out of 5 successive points are on the same side of the center line and farther than 1 sigma from it, or if a run of 8 or more in a row are on the same side of the center line, or if there is obvious, consistent, or persistent patterns that suggest something unusual about your data and your processes. Using the airport sample dataset, we will select Analyze Quality and Processes in Control Chart Builder. We are now able to drag each characteristic to the Control Chart Builder to determine if the system is out of control or not. Here we will drag the delay to the center of the Control Chart Builder and the day to the x-axis. This allows us to analyze if the delays are out of control for multiple days. Here we can see that due to the fact that there are 3 data points outside of the upper control limit on the X bar chart, we are able to say that the delays are out of control from December 22nd to December 24th. A Pareto chart is a cumulative chart that is typically used to display the distribution of root causes of defects or the type of defects. The bars on the graph display the frequency or count of each category. The line stretching across the chart displays the cumulative percent total. On the left y-axis, the frequency of occurrence is displayed, and on the right y-axis, the percent total is displayed. On the Pareto chart, the events and causes are ordered from greatest number of occurrences to the least number of occurrences. A use for the Pareto chart is the ability to determine which defects need to be solved to decrease the number of defects by a specified percentage. Using the failure size sample data, we will select Analyze, Quality and Process, and Pareto Plot. From here, we will choose the causes or defects to be the cause, process as X, and count as frequency. We can see that size is the greatest cause of defect in both processes, followed by contamination in process A and oxidized defect in process B. This being said, the Pareto plot shows us that if we wish to prevent approximately 70% of the defects in process A, we should focus primarily on solving the size and contamination issue within process A. The reliability and survivability test use the Weibull distribution, exponential distribution, and log normal distribution. This typically uses sensor data, that data describing a system passing inspection at a given time and failing the next inspection. The objective is to determine at what time the system failed between the 2 inspections. The life distribution assists in building the distributions based on the known information regarding the system. A recurrence analysis exemplifies how a recurring event occurs on a repairable system, such as an airplane or a manufacturing press. Furthermore, the support competing causes determines the effects of various causes on a failure. These various causes may include the amount of current being sent through a system, the average number of hours a system is used at a time, or the temperature at which the system is operating. Using the microprocessor sample data in SAS, we will produce a life distribution. Select Analyze, Reliability, and Survivability, then Life Distribution. We will input both the start and end time into the Y time to event and count as frequency. Here we have the ability to select any distribution to fit the model, and it has become increasingly clear that the Weibull distribution is likely the best fit. Results in the lowest archaic value, determining the relative value of the statistical model for the given set. The event plot is very similar to a timeline of the inspections. At each arrow, an inspection occurred. In between the arrows, facing each other, is when the failure occurred. However, the exact time of failure is unknown. On the compare distributions plot, the stars represent the confidence interval. Within the fans produced by the Weibull distribution, we are able to determine the probability of failure with the start time at a known time. This distribution is very useful when predicting warranties, where the hazard function will likely be used.